All right, so now we need to make the line, the potentiometric line for number 6. So given what we have, we know that it has to be before 7, right? Definitely before 9.1, but much later than 3.7. So it's got to be somewhere around here maybe, right, in this location. We know that it has to be close to 6.3, but we also know that it has to be to the right and above this 4.5. So it has to go somewhere in between these two measurements. Again, somewhere close to over here. And then down here, we know that it has to go almost completely in between 4.6 and 7.6. So my 6th line should do something like that. Pretty much, right? Maybe. Yeah, okay, good. So now number 8, we know that 8 will fall in between 7 and 9, almost right in the middle. We have no measurement for it over here, so it could go all the way here if we really wanted to, but it probably does some similar pattern to the previous ones. So we're going to assume that it continues like that, also because we have this measurement right here. So this is 7.6, this is 8.4. We know that 8 goes right in between, so somewhere around here. So that means that our line has got to do something like this. Here we're not so sure. And then we know that it has to go in between them. Okay, so a little bit closer, but pretty much what we expected. And then we'll draw one for 10. So we know that 10 is further than 9.1, but it's also less than 11. So assuming that it has a similar pattern as the previous ones, it's going to go somewhere along here. I'm going to come in between them, a little closer to 11 than to an 8.4. Okay, good. So now you have an idea based on different levels of water level taken at random spots of how to draw these lines. You know that the lines won't cross the specific points if those points aren't the value of the line. But you know how to use those values in order to put the line nearby it. You also know that you have to label the line that you drew. So I labeled 10 here, labeled 8 here, 6, 4, and 2. Okay. Okay, so this is figure 5 in your map, the one that you should complete the same way that I just showed you how in the previous image. So again, the result of that, they want you to do that with this specific map. So here I drew 2 lines first just to help you out. So because they want you to do it every 5 centimeters, your labeling should be 215 first, then 210, then 205, then 200, 195, so on and so forth. Okay, so I drew these 2. So 215, we know that the only measurement that we have that is less than 215 is 214, and as we go anywhere else in the map, everything is below 215, so 215 is very tiny. We just know that it's somewhere in this corner. Okay. Then the next line is 210. So we use all the values within the map that are a little close to 210, so somewhere between 205 and 210, and the ones between 210 and 215 in order to help us. So there's actually one value that is exactly 210, so we know that the line has to cross it. We don't see anything between 205 and 210. We do have a 207 to guide us over here, but nothing else further in the map. And here on the left we have a 206, a 208, and a 207 on the lower spectrum, meaning that 210 has to be here somewhere. And then we have a 212 and a 214 on this side. So we know that 210 has got to be in between those. So that's why I marked it over here, crossing this 210 measurement. Okay, so now you will do 205, 200, so on and so forth. So I'm going to help you a little with this 205. So 205, we know that has to be less than 106 or 206, but more than 203 or 200. So it's going to go somewhere here, somewhere in between. We also know that it has got to be less than 207, but more than 202, closer to 207. So in between them is going to go somewhere here. We know that it has to be less than 208 and less than 206, so it's going to continue on this way. right? We know that it has to be more than 203 and then 204, but less than 207. So once it crosses here, we know that it has got to go somewhere in between these, a little closer to 204. And then we know that it has to be above any of the numbers that we see here to the right. So it's going to end up somewhere over here. Okay, so you do the same thing again for all the other values. Make sure that you label them and that none of the lines cross each other. That's also a rule for these potentiometric lines. They're similar to topographic lines in a certain way. Okay, good. So that should take you through doing question 13. Okay, so now we're back to the lab manual. So the people living in the residence noticed that their well water tasted strange. After some analysis, they determined that it was some chemical commonly used in the dry cleaning process in the groundwater. So there are two dry cleaning locations in the neighborhood, and the Department of Environmental Quality thinks that one of them may be illegally dumping their chemicals-laden wastewater. So as you can see in your map, there are two different dry cleaners, dry cleaner A and dry cleaner B. So here, question 14 says, so water flows down gradient, or downhill, or down gradient in this case, right? So perpendicular to potentiometric lines. So if you think about it, it flows in a similar way to surface water did with topographic lines. So if this is a steeper or a higher elevation area and this is a lower elevation area, the contour lines will really go kind of perpendicular, looking into and out of the screen based on this location. So the groundwater will flow perpendicular to the constant elevation lines, okay? So same thing is going to happen with the groundwater flow. So it's going to flow perpendicular to the potentiometric lines, or the lines of equal water level elevation, okay? Or depth to water level. Okay, so I'm going to teach you how it is that these will look in your map using the example that we had earlier in the video. Okay, so this was our resulting map, if you would, based on what we had. So now we're going to add the flow lines, the flow path, or meaning how the water is flowing down gradient. So we know that this left part over here is upper, it's closer to the surface, and then the one that is further, that is closer to the right, is water level that is deeper and deeper. So overall, the water should be flowing from left to right in this case, right? Okay. How it's flowing, it's going to be flowing completely perpendicular to each of these lines. So if I have a water droplet left here, and I make it flow downhill, I know that when it encounters this, it's going to encounter it at a 90-degree angle, okay? Completely perpendicular. So it's going to continue that flow path until it hits the next line. And here it's not going to flow that way because that wouldn't be perpendicular, but it's going to flow a little bit further that way because that would be perpendicular. Once it encounters this one, same thing. So a little bit further that way. It continues this way, and then once it hits here, a little bit further this way. So let's see what we got. Okay, so I dropped it a little closer that way, but it's the same idea. And if I were to have another flow path from somewhere starting over here, see what it would do. Okay, good. So you get an idea of how that flow path is going to be if you drop it at a specific point. So in your lab quiz, those points where you're dropping the water from, that flow path that it should take, should be from dry cleaner A and dry cleaner B. So assume that this is a dry cleaner. How is the water going to flow from there? Same thing. This is the other dry cleaner. How is the water going to flow from there if this is the map of figure 5? Okay, so that's what you have to do. If it's not clear, again, there are plenty of examples online, but you can also use my office hours or my help session time to ask me those questions. All right. So again, after you have drawn the flow path of the wastewater from both dry cleaner A and dry cleaner B in the neighborhood, you may need to talk to your instructor, blah, blah, blah. So that is what you have done in question 14. And now you can go ahead and answer question 15 and so forth and so on. So question 15 asks, which one of the two dry cleaners is likely dumping their wastewater rather than disposing of the chemical-laden water properly? And how can you tell? So ideally, once you have drawn the flow paths coming from either one of them, one of the flow paths is going to be closer to the residents than the other one. And so that is how you pretty much know, because the residents were the ones who tasted the water and they thought it was strange. So if the flow path of one of them, of the dry cleaners, goes nearby the residents, it's more likely that it will be from that dry cleaner than the other one. Okay, good. So, number 16. A hydrologist wants to calculate the amount of time that it takes for a contaminant to leave the entire watershed. So to do so, she puts rhodamine, I'm not sure how you say it, dye in the stream at point X. So point X in your map is all the way to the top part of the map. It's on the stream itself. And she detects that the dye at point Y about 3.5 hours later. So what point Y is at the bottom of the map. So the time that it took it to go from point X to point Y was 3.5 hours. So now they're asking you, how fast does water in the stream travel? And this has got to be a unit of meters per hour. So the way you do that is you measure the distance between X and Y, and then you divide that by the hours, right? Meters per hour. So here they also give you a legend in the map. They say that 1 centimeter is equal to 100 meters. So you have to use a ruler that has centimeters on it, not inches, or you can use inches and then convert it to centimeters. And you don't want to measure it completely straight. You want to measure it following the path of the stream, okay? Or else you're going to get a little bit, what would it be? Lower number than I want you to get. So make sure that you follow the path of the stream to measure the distance between X and Y, and that number, again, converted to meters, and then divided by the amount of hours that it took for the rhodamine dye to get from point X to point Y. You come up with an answer and you give it to me in the quiz. All right. So question 17. So some of the rhodamine dye from question 5, or that should be again question 16, not question 5. Some of that rhodamine dye entered into the aquifer. So it infiltrated through the ground and it made it into the aquifer. That rhodamine dye was detected in well Z. So point Z is also towards the bottom leftmost part of your map. And it was detected 83 days after it was introduced into the stream. How fast did the groundwater travel from where it was input to the system at well X? Or sorry, I think that should be to the system at well Z. So how fast did it travel from when it infiltrated at point X all the way to point C? Okay, so the way you do that is you use a similar concept. So you use 83 days, you convert that to hours, so hopefully you know that conversion. And then you use the distance between point X and point Z using the flow path. So again, the flow path should be perpendicular to the equal elevation of water lines. And then again, using that distance in meters divided by the hours that you will have converted from days, you'll get an answer here that will also be in meters per hour. Okay, and you'll answer that in the quiz. Okay, lastly, what does the difference in rates between questions that should be 16 and 17 tell you about the differences in travel time between groundwater and surface water? So these two will give you a rate. So what does that rate from either one, how do they compare? And what does that say about the flow of water at the surface versus the groundwater? And then later on you have to elaborate and explain how this might be important in the real world. So, and based on that also, you have to calculate something else. So, approximately how long after the cleaners is shut down would the residents need to rely on an outside water source? So using the rate that you found over here, you have to find the distance between the dry cleaners that is dumping their waste into the groundwater and that distance between that and the residence. And based on that distance and the rate that you had found over here, calculate the hours or days that it would take for the residents to be relying on outside water that is not contaminated, so that they don't get poisoned. Okay,